We are now moving on to unit number 4, which is titled vectors. So vectors are quantities that have magnitude as well as direction. Displacements are the simplest example of a vector quantity, and in order to define a vector, you need to state its magnitude as well as its direction. On the other hand, there are what we call scalar quantities, which only have a magnitude, such as temperature, pressure, energy, as well as mass and time. The way that we represent vectors is through the use of arrows, and typically we have a starting point as well as an ending point where we draw the arrowhead. And the beginning point is irrelevant, only the displacement matters. So it doesn't really matter where the vector begins. All that matters is the length of the vector as well as the direction that it points towards. So vectors can be added, and so in order to add two vectors A as well as B, what you do is you connect the tail of one vector to the head of the other vector. And in order to find the sum of these two vectors, A plus B, you draw a vector from the initial position all the way to the final position. So A plus B is a single vector that is equivalent to the effect of A followed by B. Or we can add it in the other order. So we can start with vector B, connect to it vector A, and we will still get the same B plus A vector, which is actually equivalent to A plus B. So we can use what we call the parallelogram rule, which is to take the parallel of vector A and the parallel of vector B, connect it to the other vector, and what you form is a parallelogram where the resultant vector is a diagonal through that parallelogram. In order to subtract vectors, we use the negative of one of them. So if we have the vector B plus the negative of vector B, this will equal 0. We can draw a diagram for this, where we have the vector B pointing downwards. Therefore, vector negative B will be the same size, but in the opposite direction. Also, if we have a vector A, as well as a vector negative B, if we add these together, we have A minus B, which this vector here, this can also be written as A plus negative B. So addition and subtraction can always be done graphically, as we have just shown above, but we can also describe these vectors in terms of their components relative to a coordinate system. Say, for example, we have the xy coordinate system right here, and we have a vector A which begins at the origin, and it has a length A. We also have the angle theta, which goes from the horizontal positive x-axis all the way up to the vector A. Then we can project from the vector A down onto the x-axis to have the x component of vector A. We can also project from the vector A to the y-axis to have the vertical component, which is AY. Now AX is called the x component, so that is the projection of A onto the x-axis. AY is the y component, which is the projection of A onto the y-axis. We can also come up with a few formulas using Sol katoa. First formula is AX over A, which is equal to cos theta. So that is using the cos is equal to adjacent over hypotenuse. Or we can rearrange this to get AX is equal to A cos theta. Using SO, sine is equal to opposite over hypotenuse, we have AY over A is equal to sine theta. Or this can be rearranged to get AY is equal to A sine theta. So AX and AY, that is what we call the components of the vector A. And you can also use the Pythagorean theorem to go the other way. So if you know AX and AY, you can find the original vector A by taking the square root of the sum of the square of AX plus AY. So this gives us the magnitude of the vector. We could also find a direction using tan theta, which is equal to sine theta over cos theta. That is one of the identities you learn in mathematics. So this is going to be equal to AY over AX. Now we're going to take a look at a special vector that we call a unit vector. And this vector here has a length 1 and it is parallel to the axis. So we have a unit vector I hat along the x direction. For the y direction we have j hat, and for the z direction we have k hat. So if we draw a diagram here, we have the y and the x-axis. We also have the z-axis which comes out of the page but is not shown in this diagram. So let's say we have a vector A that goes like this. Therefore, the I hat vector goes along the x-axis and has a length 1. The j hat vector goes along the y-axis and has a length 1 as well. And the k vector, which will not be shown properly here, but it comes out of the origin, out of the page, that will also have a length of 1. Then we can define the vector A in the xy plane as being written as A vector, as being written as A is equal to AX I hat plus AY J hat. Or more generally, any vector. So this vector can be in the 3D plane. So this includes x, y, and z axis as well. This can be written as the x component I hat plus the y component j hat plus the z component k hat. Alternatively, you can make it a bit more simple. Just write it as, instead of ijk, you can use x hat, y hat, z hat. So it can be written as x hat plus y hat plus z hat. And so the reason that we write it in component form is that it makes it much easier to add these vectors together. And the way we can add them is we can add by components. Say, for example, we have two vectors here. We have vector A, which is equal to AX I hat plus AY J hat. We also have a vector B, which is equal to BX I hat plus BY J hat. If I were to add these two vectors together, I would have A plus B is equal to AX plus BX I hat plus AY plus BY J hat. So this is just a way of adding the components separately. Say, for example, we have two vectors, A and B. So vector A has a length of 10 units, also has an angle of 20 degrees. Vector B has a length of 6 units and an angle of 130 degrees. Now, if we were to break up vector A into its x component, we have A, x is equal to A cos of 20 degrees, which is equal to 10 cos of 20 degrees, which gives us 9.397. The x component of the vector B is equal to B cos 130 degrees, which is equal to 6 cos 130, which gives us a negative 3.857. Now, the x component of the resultant vector C, this will be equal to the sum of the x components of A and B. And so summing together 9.397 minus 3.857, we get 5.54. Now, if we look at the y component of AY is equal to A sine 20 degrees, which is equal to 10 sine 20 degrees, equal to 3.42. BY is equal to B sine 130, which is equal to 6 sine 130, which gives us 4.60. So therefore, the y component of C is equal to AY plus BY, which gives us 8.02. So we can write our resultant vector C is equal to 5.54 I hat plus 8.02 J hat. Now we take a look at something that we call the scalar product of vectors, that is also called the dot product. So we define dot product as the symbol right here in the middle, A dot B, and this is equal to AB cos of phi. And one thing to note is that this will always give us a scalar answer. And this is related to the projection of one vector onto the other. So if we draw a diagram, so let's say we have a vector A and a vector B, then the projection from vector A onto vector B at an angle of phi, this is what we call A cos of phi. And now let's take a look at the three cases of different angles. So when phi is equal to 0 degrees, then A dot B is equal to A times B, which gives us the maximum possible value for the dot product. And what this represents is two vectors that are parallel. So just think about the angle theta. Remember, the angle phi is the angle between the two vectors. If the angle between them is 0, that means that the two vectors are parallel. Now, if the angle is 90 degrees, then A dot B will give 0. And so this is a value when the vectors are perpendicular to each other, or at a right angle to each other. The last case is when phi is equal to 180 degrees, and what we get is A dot B will give us negative AB. And so this is the lowest value we can get. And what this means is that the two vectors are anti-parallel. So what this means is that they are parallel, but in opposite directions. Now for unit vectors, if we take the dot product of unit vectors, I hat dot I hat, this is going to be equal to j hat dot j hat, which is also going to be equal to k hat dot k hat, which gives us 1. Also, if we take the dot product of I hat and j hat, which is equal to j hat dot k hat, which is equal to I hat dot k hat, which gives us 0. Now for any vector, let's say A, which is given by the following components, and a vector B, which is given these following components as well, then if we were to take the two dot products, this is the result we should get: AX BX plus AY BY plus AZ BZ, which is also equal to the formula we stated above, which is AB cos phi. And so always remember that this is going to be a scalar result. So we use this formula to find the angle phi between the vectors. Now let's move on to what we call the vector product, also known as the crossed product. And the thing to note is that this will always give us a vector answer. So the formula I want to take a look at is written like this. So we have these two long bars at the side, which we call the magnitude. So the magnitude of A cross B, remember that A cross B is a vector, but we are only taking the magnitude. And so this is actually going to be equal, it's going to be very similar to what we saw above, except this one here is AB sine phi. So this is different from AB cos phi, which is for the dot product. And when phi is equal to 0 degrees, the magnitude of the cross product of AB, this is going to be 0. And this represents parallel vectors. When phi is 90 degrees, the magnitude of the cross product AB is going to be equal to A times B. So this is the maximum value, and this occurs when the vectors are perpendicular to each other. And the last case is when phi is 180 degrees, so the magnitude of A cross B is going to give 0. And this means they are anti-parallel vectors. Now for unit vectors, if we take the cross product of unit vectors, say for example I hat and I hat, this is going to be equal to j hat and j hat cross product. And this is also going to be equal to the cross product of k hat and k hat, which is 0. Now if we were to take I cross j, we get k. J cross k, we get I. K cross I, we get j. Now if we were to swap around the order, so if we start here at the top, we swap and go j cross I, we get the negative answer, which is negative k. If we swap this one here, we get k cross j, we get negative I. And if we were to swap and take the cross product of I and k, we get negative j. That is the end of Unit 4.